from the brief introduction to the subject dynamics of machines, we have seen that machines are primarily interconnected rigid bodies. So, therefore, if we have to study the dynamics of a machine, the first thing we have to understand that how rigid bodies behave under load or under forces. That is, studying the motion of rigid bodies forms the first step towards the subject dynamics of machines. So, therefore, we will start today studying the motion of a rigid body. Now, rigid body motion can be studied under two headings. The first, the simpler case, which we call plane motion. And the more complicated type of rigid body motion we call space motion. Now, when we call the motion of a rigid body to be a plane motion, it is the situation where all the particles of a rigid body, they move in different directions, no doubt, but at any instant of time all the velocity or displacement vectors lie in one plane or in parallel planes. On the other hand, in case of a space motion of a rigid body, the velocity vectors of different points will not lie in different directions or lie in the same plane or parallel planes. So, studying plane motion is much simpler, as you can see, because we can project the whole motion parameter, all the motion parameters like velocities, displacements, accelerations on a projecting plane or the plane of the paper. Next, I think let us see again in plane motion what are the different possible types you can have. So, in plane motion, let us first study plane motion. What are the typical examples? Say a wheel rolling on a horizontal surface. So, here you know that the velocities of different points will be different, but they will be all lying in parallel planes. Similarly, we can have another example. If you hinge an object and suspend it by two equal links, then again we know that this object will undergo a motion which you can call plane motion. But again there is a subtle difference between these. I will take another simpler case where a wheel is rotating about a fixed hinge. So, in that case the velocities of various particles will be like this. So, there are three types of plane motions, as you can see here. One is where all the particles on the rigid body, they have exactly same velocity, same motion, identical situation. In another case, it is a more general situation. It is neither a pure rotation like this nor a pure translation like this, but a general motion. So, for example, if we take our familiar example of a slider crank mechanism, which we have discussed in our first introductory lecture. Now, if we study the three rigid bodies which are interconnected and they are moving, and you can see that this particular rigid body, which we call crank, is undergoing a pure rotation about a fixed point, hinge point O. This particular rigid body is undergoing a pure translatory motion like this, whereas this one is undergoing both rotation and translation, that is a general type of motion. So, a machine consists of a number of rigid bodies interconnected, and each one of them undergoing different types of motions. Of course, as I mentioned earlier, in this particular example, all the particles of the system, they have their displacements, velocities and accelerations lying in parallel planes, so that the whole motion picture can be projected onto the projecting plane. Now, the simplest of all this will be a case of translation. It is a rigid body where each point of this rigid body, they have exactly same displacement, same velocity, same acceleration. So, effectively what we can do then, that this is more or less equivalent to a particle with the same velocity or displacement as this rigid body, but the total mass of this is same as the mass of this particle. So, therefore, cases of pure translation, a rigid body may be considered to be concentrated in a particle with the same displacement parameters, velocities and acceleration. This is pure translation. Now, translation can be again of two types. This is a translation which we call rectilinear translation. Why? Because we find the path of each particle is in a straight line. That means, it was here, it has gone there, it was here, it has gone there, it was here, it has gone there, it was here, it has gone there. There is another kind of translational motion is possible, where each particle of a rigid body undergoes a different kind of trajectory, which is not a straight line, but the same for all. That means, a particle which was here, it has gone here, particle which was here, it has gone here, particle which was here, it has gone here, and so on. So, here also at any particular instant of time, the velocities of the particles will be all identical, but the trajectory of the particles will not be straight lines like this. So, this is called curvilinear translation. The simplest type of motion, that is translation, can be either rectilinear or curvilinear. In both these cases, since at every instant all the particles undergo identical motion, we can treat the whole body as one single particle like this, of the same total mass as this original one. Next, let us consider an example of space motion. Before I proceed further with the case of plane motion, it is also appropriate for us at this instant to understand what we call by a space motion or three dimensional motion. Now, the simplest example of that will be a spinning top with which we are familiar. We know that this top undergoes a spinning motion at a very fast rate, and the axis of this undergoes a precessional motion about a vertical axis like this. So, in this case we will find that no point on this body, or rather all the points on this rigid body, their velocity vectors, acceleration vectors, etc., at any particular instant of time do not lie in a single plane or in parallel planes. So, this is a very common example of space motion, but even in engineering we have cases where a particular system will undergo a motion where the velocities, displacements and accelerations of the various points do not lie in the same or parallel planes. Now, let us come back to our study of plane motion, primarily because a very large number of engineering systems undergo parallel motion problems. As for example, we have shown our slider crank mechanism. Even if we take a simple crank follower mechanism, here again we will see that all particles of describing this system, they undergo motion where the velocities, displacements and accelerations lie in parallel planes. We can have motion of a gear or a wheel transmitting power between two shafts. Again you will find that all the points undergo motion where the motion parameters lie in parallel planes. So, there are a very large number of engineering problems or systems which involve plane motion, and so let us first start studying the problem of systems involving plane motions. Before we start studying the plane motion problems of a rigid body, so let us see that how the description of a rigid body has to be done, or rather how we describe the motion of a rigid body in plane motion. So, the next thing we will study in little depth is what I mean to say, that one object is here and after some time I find it has gone here. So, this is the start and this is the end or finish. How to describe the motion of this rigid body? In case of particle, there is no problem. If motion of a particle, it was start here and end here, I can simply say that the displacement of this motion is this much and denoted by a vector. But in this case, it constitutes a large number of particles and each particle may have different displacement vector. For example, suppose if we take this point its displacement is this much. If we take this point, its displacement is this much. So, they are different. So, if this is called S1 and this is S2, then we know S1 is not equal to S2. So, how to describe the motion of such rigid bodies? That is what is our problem. To do that, let us see that how we describe the motion of a rigid body. First, let us take this rigid body. I am drawing a simpler object, a simpler body for better understanding, and the same body goes there. So, we can generally, it can be shown that we split this motion into two parts. How? First, we take any point here. So, let us for example, consider this as the reference point. It can be any point on this. So, this point P initially has gone to this point as P f. So, this point's displacement is this, and if we just subject this body to a pure rectilinear translation, then the position of this body would have been like this. So, this is a pure translation, rectilinear translation of the body from the initial and intermediate position, and then keeping this reference point whatever I have selected, we give a rotation to the body from this position to this position. So, this is the translational part and this is the rotational part. So, any motion of a rigid body can be split into these two pure motions, pure translation and pure rotation with one point fixed, and that will provide us the general motion of a rigid body. So, now we will find out the effect of a force on a rigid body, because ultimately, as you know, that our objective is to find out the effect of forces on a machine, or the kind of forces are generated by motions of machines and machine parts and such things. So, therefore, now let us start the effect of force or a system of force on a rigid body which is in plane motion. So, we again take our rigid body and say this is being acted upon by a number of forces, large number of forces, which can be all ultimately combined to make this resultant of all the external forces F, which is acting like this. Now, this rigid body is acted upon by this force. Our objective is to find out that what is the motion of this. Now, We will not go back to the basic fundamentals, because that is a subject which you have studied in dynamics, or this kind of topics or problems you have solved in dynamics. We will not go into the basic fundamentals of that, but certain important points we will recapitulate little bit for going further. Now, you have seen in basic dynamics courses that motion of a rigid body due to a force can be found out in the following manner. First, what we do, we identify a particular point which we consider as the center of mass. What is the center of mass? The center of mass means that for the definition of a center of mass of a rigid body, I will show you here. This is C. So, if you take any particle whose mass is a delta m I and which is located at a position rho I, then if you sum up this product for all the particles, it will result in 0, if C is the center of mass. This we have to keep in mind. That is the definition of center of mass. Or if you consider that if you take the moment of all the masses about any other point, it can be considered to be the moment of all the particles about this, about an axis passing through this, plus the whole mass considered to be concentrated here and its moment about that. We will look into it later. First, now go back to our problem. So, this force which is acting at a distance E from the center of mass, what we can do now is we can apply an equal and opposite force here, minus F and plus F. So, then this becomes equivalent to a force passing through this and a moment acting on this, which is given by F into E. Now, you will notice that I have not put a moment vector here, because in plane motion all angular activities like whether angular velocity, angular displacement, moment, they can be represented by algebraic quantities. Say we may consider that if it is in the clockwise direction they are positive, if they are anti-clockwise direction they are negative. So, their summing up or subtraction becomes, or it is just like an algebraic quantity, whereas force, its directions are different, and so they need to be represented by vector. So, now if the mass of total mass of this be m and second moment of the mass, that is moment of inertia of the body about an axis passing through the center of mass is moment of inertia about the center of mass I, then this force will cause an acceleration in this direction of the center of mass, which is A, and it will cause an angular acceleration alpha due to this, and their quantitative dependence will be, this will be equal to F divided by mass, and this will be m divided by IC. So, therefore, any set of forces on a rigid body in plane motion can be considered to be the effect of a single resultant force on that rigid body, which in turn is equivalent to that force acting through the center of mass of that body and a moment acting about the center of mass, which is given by the force and the product of the force and the eccentricity of the force, which causes the motion of the rigid body in this following form, that the center of mass is accelerated, which is given by this, and the body possesses or gets an angular acceleration alpha, which is given by this, about the axis passing through this. So, that means what we are doing, that this rigid body its motion is being described as the acceleration of this center of mass and angular acceleration about this center of mass, about an axis passing through the center of mass, which we call c. Now, as you know from your basic courses in dynamics, that a rigid body, if a particular point, the center of mass, which plays a central role, its velocity or its acceleration and angular acceleration about an axis passing through this is given, that completely describes the motion of this rigid body. If the initial conditions are known, we can find out the initial or final values. So, for example, if we say that initially its velocity was v0 and its angular velocity was omega 0, then at any instant of time the velocity, or after a time dt, v will be v0 plus a delta t and omega will be omega 0 plus alpha into delta t. So, therefore, we can proceed ahead and we can get the velocity at any instant of time if we know the initial conditions, because of this acceleration, linear and angular accelerations. So, this brings to the end of the case of a single rigid body under the action of a set of forces, and what motion, that means what accelerations are developed, we find out like this. Next, let us find out how we use this, or how we consider this particular aspect what we have just discussed in studying the forces which are developed in various machines. Now, as I mentioned in the introductory lecture, that a body when is in motion, that means when which is accelerated, so then the system is subjected upon or subjected to or is acted upon by certain dynamic forces which are because of the inertia forces of the system. To explain this little bit more, let us consider this case. The simplest case will be again our slider crank, and then we will go to more complicated examples. This is a very useful mechanism, that is why we are using it in so many problems, the same thing. Now, here I tell that this is a pure rotating body about its fixed hinge here, and let its moment of inertia about this fixed hinge be I. Let us consider this is a pure reciprocating or rectilinear motion body. So, I have to give only mass of this. Now, if and the length of this rod is L, radius of this crank is R, and at any particular instant which is shown here like this is theta, and say it is being rotated at a constant angular velocity omega. Then if we have to design say this particular rod, say just our interest is that, how do you do it? Now, you will first what we will do is that we have that this particular rod, if it is massless, for simplicity, then it will be subjected to either pure tension or pure compression. So, it will be subjected to either pure compression or it will be subjected to a pure tension, which means that resultant force on this will be 0, because it is a massless system, it cannot sustain any resultant force or moment. Now, when this is, we can from kinematics you have already found out that the acceleration of this body at this instant will be A. If that be the situation, then you know that this particular point, that means this rigid body must be subjected to a force in this direction, which is mass into acceleration. That means this body, its acceleration is A. So, resultant force on the body must be also then F, which is simply mass into acceleration, but we know that this body is acted upon by these forces. One is a force from the support, and either from this side, in this particular case it will be from this side. So, let me correct my drawing. So, it can be from this and a force which must be acting along this, because this rod cannot have sustained any force here which is not in the line of this. So, it has to be, if this angle is beta or phi, so this angle has to be also phi. Now, how much will be this force? That we can find out from this equation, that P cosine phi must be equal to mass into acceleration, or this force P will be mass into acceleration by cosine phi. We can find out this reaction because there is no movement along this direction which is perpendicular to these slider surfaces. So, total force in this direction will be 0. So, we can then write that R minus P sin phi is 0, that is R will be equal to simply P sin phi. So, therefore, we know that this connecting rod, which is massless in our this example, has a force P in this direction. So, obviously, here also therefore, it must be acted upon by an equal and opposite force P, so that the system or this rod is under no resultant force. Now, this is a particular example, and we solve the loading on the connecting rod as just a simple case of example, but I think this is just from the basic fundamentals we try to develop the procedure by which you could find out the force. But while dealing mechanisms with many members, more complex motion, a better, more generalized approach of analyzing forces on various members at various contacts, at various hinges, it will be necessary to develop that methodology, and we will next try to develop that methodology. Now, before taking up the problem of a generalized mechanism and the problem of finding out the various forces, moments at various surfaces, then the contact forces at the hinges and so on, we will see that it will be convenient to consider the dynamic problem after we convert the dynamic problem into a static equilibrium problem. What I mean to say is this, that any system under motion, in general motion, then if it is in dynamic equilibrium, it means that it is running under the influence of some forces, then each and every member of the mechanism will be subjected to some forces which are acting on it and which are producing the necessary or rather the resulting motion parameters like accelerations, both angular and linear. Now, if I say that a system or a mechanism or a machine is under static equilibrium under the influence of certain forces, what does that mean? Say for example, if we consider this case, a 4-link mechanism with the ground link fixed. I state that under the action of this moment, this force and this force, this system is in static equilibrium. If I tell that, it means that no member will have any motion when these moments and forces are acting. Now, if the whole system is motionless, it implies that each and every member of this mechanism or system is in equilibrium. That means this link, which I think in your terminology you have termed it as link 4. So, fourth link, which is subjected to this external force, we call it say F4, and there will be 2 hinge forces, reaction forces, and one reaction force from here, another reaction force here, we call it 1 4, and this I call R 3 4. Then the combined action of this reaction force and the externally applied force is to keep this system under static equilibrium. Similarly, this particular link, which we call the connect coupler, or this, under the influence of this force, which we call F3, and the reaction forces like this, it will remain under static equilibrium. That is, each and every member of this mechanism will be in static equilibrium under the action of the external forces acting on that particular member. So, this philosophy or this principle we can use in solving the dynamics problem. In the next lecture, I will explain the technique of converting a dynamics problem into a static equilibrium problem and illustrate it with the help of an example.